Hello everyone, my name is Michael Casey, and today I'd like to talk about linear dimension reduction approximately preserving a function of the one norm. This is work for my PhD thesis at Duke last year. The Johnson-Lindenstrauss lemma from 1984 may be stated as follows. We are given a finite point set X in a possibly very high dimensional space. However, there exist linear maps F down to Rk that approximately preserve the 2 norm. The approximation holds for all pairs of points in X, provided that the target dimension k is large enough. It need not be too large in the sense that it only grows like the log of the point set size. The proofs are probabilistic, showing that for a random matrix F with, say, IID Gaussian entries, the approximation holds with high probability. People appreciate this lemma because no other geometric assumptions are made on the point set X. The 2 norm is a nice norm, and so is the 1 norm. So people have asked if there's an analogous result for the 1 norm. However, Lee and Naor in 2004 and Brinkman and Charikar in 2005 gave explicit examples of point sets equipped with the L1 metric, such that if there were such F setting them down to Rk and preserving the 1 norm like so, even if the F were nonlinear, the target dimension k must grow roughly like the square root of the point set size. When n is large, this is a much larger target dimension than that of Johnson-Lindenstrauss. These point sets are based on the vertices of so-called diamond graphs. These are constructed recursively, beginning with an edge and replacing each edge by a force cycle up to some level. The graph is equipped with its path metric structure and embedded in L1. The reason the target dimension k has to be so large is because we are requiring that these blue diagonal distances, when measured in Rk, still approximate their path metric distances in the original graph. So if we wish to preserve 1 norm information but have a target dimension k much closer to log n, we need to modify the original problem in some fashion. We propose to do so as follows. We change the metric on the target space Rk to ρ, and we only ask to preserve a function mu of the 1 norm. We want mu to be non-negative, concave, and strictly increasing, so that not only is mu invertible, but mu after the 1 norm induces a metric on Rd. We want our metric ρ to be translation invariant, and you want the target dimension k to not grow too quickly in the log of the point set size. We've been able to achieve such a result almost completely by using random matrices with IID Cauchy entries. Our metric ρ depends on this function xi, and we set mu to be the expectation of xi. We can then approximately preserve the function mu of the 1 norm, even taking the error inside mu. Because mu is invertible, this means we can approximately recover the 1 norm itself. We can do so for all pairs of points that are not too close. In principle, because the point set is finite, we can always rescale it to ensure this condition. In particular, we can do such a rescaling for the diamond graph examples. Here, however, the target dimension k is logarithmic in the point set size. In practice, this condition might still be difficult to verify, and so one can ask what happens for smaller distances. If you move the error back outside mu, we can have this approximation hold for all distances down to 8 epsilon squared. The target dimension k is still logarithmic in n, but now it grows a bit faster as epsilon decreases. We shall say more about this log 8 epsilon squared dependence a little later. Pushing for even smaller distances, we could only recover a lower bound, down in this region, and the target dimension k is quadratic in the log. We believe this may be an artifact of the proof, though. For the rest of the talk, I'd like to explain the choices for Cauchy, xi, mu, and ρ. So why Cauchy? Because of the 1 stability property. If you look at the coordinates of a projected point, they will be random, but they will actually be Cauchy distributed with the 1 norm out front. This makes our metric ρ an empirical mean that depends on the 1 norm. If we marginalize out the Cauchy dependence, then we recover a deterministic function mu of the 1 norm. The task is to show that rho concentrates about mu. This means it stays close to mu with high probability. One usually proves such results by using exponential Markov inequalities. We multiply by s times k, exponentiate, and apply Markov. The IED assumption allows us to take k outside, and we are left to estimate a single moment-generating function. However, Cauchy random variables only have finite fractional moments, so the presence of Cauchy in the exponential forces xi to not grow too quickly in its input. In fact, xi can grow at most like the log of fractional powers of its input, so we chose xi accordingly. It is strictly increasing and concave, with the plus ones ensuring that it is 0 at 0 and non-negative. This makes xi a non-negative subadditive function, and so it plays nicely with the triangle inequality, ensuring rho is a metric. Because mu is the expectation of xi, it inherits this non-negative subadditivity, so that mu after the one norm induces a metric on the original space. We want our concentration bounds to be as independent of the distance lambda as possible. We have shown that they can look like so, with t squared depending on mu lambda, v squared as an upper bound of either the second moment or the variance of xi, and a an auxiliary function that may also depend on lambda. We have chosen xi the way we have to make all these dependencies on lambda as explicit as possible, so that we can control this tail bound in each of the big, medium, and small regimes. In particular, our choice of xi gives us an explicit function for mu. Mu behaves like root lambda when lambda is small, and log lambda when lambda is large. This log lambda behavior allowed us to move the error inside mu for the big regime results. Those results also depend on the variance being bounded independent of lambda. For finer control when lambda is small, we can bound the variance by this function, which can be made explicit in lambda, and it gives rise to the log A epsilon squared dependence we saw in the target dimensions for the small and medium regimes. To finish with a proof sketch, we split the moment-generating function into two terms. A second-order Taylor expansion of the exponential gives us a bound quadratic in S and depending on the variance, and integrating by parts the other term can eventually give a bound quadratic in S. The goal is to show that this tail probability decays exponentially in t. Our choice of xi helps us do this because we can upper bound this tail probability by this one, invert the log to recover something exponential in t, and then use the explicit formulas for the Cauchy density and tail probability to show that this tail probability decays exponentially in t. We can finally optimize in S to achieve our tail bounds. Here are the references. My email is here. Thank you so much for listening.